There is, there is a fire waiting to happen inside your kitchen, and the odds are high that you have no idea it is there. According to the National Fire Protection Association, cooking equipment is the leading cause of home structure fires in the United States, and one of the most frequently overlooked fuel sources feeding those fires is not the stove itself. It is the saturated, oxidized hydrocarbon-rich grease filter sitting directly above it, that mesh filter, the one you almost certainly have not cleaned in months or possibly years, is not just an aesthetic problem. At a certain saturation point, it becomes a genuine ignition risk. One flash of heat traveling upward through a clogged filter loaded with oxidized lipids can ignite a grease fire inside your ventilation duct. And that is a fire your kitchen extinguisher cannot easily reach. But here is what is interesting. The same chemistry that makes grease so dangerous is also what makes it surprisingly easy to remove, if you understand how it behaves at a molecular level. And that is exactly what this video is about. Not just the pour and soak advice you have probably already heard. Mason is going to walk you through the actual science of why your $3 pantry ingredients dissolve years of carbonized grease in under 7 minutes, and how to do this the right way so it never builds back up this fast again. If you want molecular-level cleaning knowledge that actually makes your home safer and easier to maintain, subscribe to Mason Pure Cleaning and hit the notification bell. Every week, the chemistry behind your toughest cleaning problems gets broken down into actionable steps anyone can execute. Understanding the enemy, what grease actually is, before the solution makes sense. The problem needs to be understood properly. Most people treat grease as just dirt. It is not dirt. Grease is a complex organic compound, specifically a mixture of triglycerides, fatty acids, and polymerized lipids that have been exposed to sustained heat. When cooking oil or butter heats up in a pan, it releases aerosolized lipid droplets into the air. Your range hood pulls those droplets upward, and the aluminum or stainless steel mesh filter intercepts them. This is the filter doing exactly what it was designed to do. Initially, those lipid deposits are soft, golden, and relatively easy to wipe away. However, when they are left in place and exposed to repeated cycles of heat, airflow, and oxidation, something chemically significant happens. The fatty acid chains in those lipids begin to cross-link and polymerize. This is the same process that makes linseed oil harden into a paint film. The grease transitions from a soft lipid state into a rigid, hydrophobic polymer, essentially a plastic-like coating bonded directly to the metal mesh. At this stage, water alone cannot touch it, and standard dish soap applied cold has very limited effectiveness. The grease has essentially cured onto the surface. This is why scrubbing with a sponge gets you nowhere. You are not dealing with a substance that responds to mechanical abrasion at room temperature. You are dealing with a polymerized organic coating that requires a specific chemical environment to break down. That environment involves alkalinity, heat, and surfactant chemistry working simultaneously. And in a moment, that is exactly what will be built. Know your filter. Aluminum vs. stainless steel. There is one important material distinction worth addressing before touching any cleaning solution to your filter. Range hood filters are manufactured from two primary materials, aluminum mesh and stainless steel mesh. This distinction matters because the two metals respond differently to alkaline cleaning agents. Aluminum is a reactive metal. It is lightweight, affordable, and extremely common in residential range hoods. However, aluminum has a known vulnerability to highly alkaline substances. Prolonged exposure to concentrated sodium hydroxide, the active ingredient in heavy-duty degreasers and commercial oven cleaners, will oxidize and pit aluminum surfaces, leaving them with a dull, chalky appearance or even causing structural weakening over time. This is why professional-grade degreasers carry warnings against use on aluminum. Stainless steel, by contrast, is considerably more chemically resistant. Its chromium oxide passive layer protects it against oxidation and makes it far more tolerant of alkaline cleaning solutions without surface degradation. The method being used here, baking soda and dish soap in hot water, sits at a mild alkaline pH of approximately 8 to 9. This is gentle enough to be safe for aluminum filters, while still being chemically active enough to break down polymerized grease. It is one of the reasons this particular combination is the recommended approach rather than reaching for something stronger. Using overly aggressive chemistry on an aluminum filter is a mistake that damages the very thing being cleaned. If you are uncertain which material your filter is made from, quick magnet test will confirm it. Stainless steel is magnetic in most grades, aluminum is not. The science of the solution, molecular level breakdown. This is the section that separates this explanation from every generic baking soda hack video on the internet. Understanding what is actually happening chemically is what allows someone to execute this correctly every time and troubleshoot the rare case where extra effort is needed. Hot water, the thermal catalyst. Heat is not just a comfort element in this process. It is a critical chemical accelerant. Grease, even in its polymerized state, has a thermal softening point. When exposed to water above approximately 60 degrees Celsius, and boiling water sits at 100 degrees Celsius, the cross-linked lipid polymer begins to soften and lose some of its structural rigidity. Molecular vibration increases, weakening the bonds between the grease matrix and the metal surface. Heat alone will not dissolve the grease, but it creates the physical conditions necessary for the chemical agents to penetrate the deposit rather than simply sitting on its surface. Baking soda, the alkaline saponification agent. Baking soda, chemically known as sodium bicarbonate, is the scientific workhorse of this formula. When dissolved in hot water, sodium bicarbonate releases carbonate ions that raise the pH of the solution to approximately 8.3. This mildly alkaline environment triggers a process called saponification, the chemical conversion of fats and oils into soap and glycerol. Saponification is the same fundamental reaction used in soap manufacturing. Lye, strongly alkaline substance, is reacted with animal fats to produce soap. Baking soda does the same thing at a gentler, slower pace, which is exactly what is needed here. The alkaline environment breaks the ester bonds that hold the fatty acid chains together within the polymerized grease structure. As those bonds are broken, the formerly solid grease deposit is converted into water-soluble soap compounds that can be rinsed away. The grease is not being physically scraped off the metal. It is being chemically converted into something that dissolves in water. This is the fundamental reason this method works where scrubbing alone does not. Dish soap, the surfactant bridge. Dish soap contributes the surfactant layer to this cleaning equation. Surfactant molecules are uniquely structured with a hydrophilic head that is attracted to water and a hydrophobic tail that is attracted to oils and grease. When dish soap is added to the soaking solution, surfactant molecules position themselves at the boundary between the loosened grease particles and the water. Their hydrophobic tails attach to the grease. Their hydrophilic heads face outward toward the water. This creates a molecular encapsulation called a micelle, a tiny sphere in which a grease particle is completely surrounded and suspended in water. Once encapsulated in micelles, grease particles can no longer re-adhere to the metal surface. They remain suspended in the water and wash away completely during the rinse phase. When these three agents are combined, thermal energy from boiling water, saponification from baking soda, and micellar encapsulation from dish soap, the result is a cleaning system that attacks polymerized grease from multiple chemical angles simultaneously. This is not a marketing claim. This is applied chemistry, and it is why the method works in 7 minutes on deposits that years of scrubbing never successfully removed. What you need: the $3 supply list. Everything required for this restoration costs roughly $3, and the probability is high that it is already inside your home. A large pot or roasting pan, large enough to fully submerge or at minimum fully cover the filter when laid flat. A standard kitchen roasting pan is ideal. If the filter is too large for any available pan, the kitchen sink works if sealed with the stopper. though a dedicated container provides better temperature retention. Boiling water, filled to sufficient volume to completely cover the filter. Temperature maintenance during the soak matters, so boiling rather than simply hot tap water is essential. Baking soda, a quarter cup per session. Standard sodium bicarbonate, the same box used for baking or refrigerator deodorizing. This is the primary saponification agent. Liquid dish soap, 1 generous tablespoon. Any commercially available dish soap formulated for grease-cutting performance will function effectively in this solution. Rubber gloves, to protect hands from the hot solution and the cleaning agents during scrubbing. A soft bristle brush, an old toothbrush or a small kitchen scrub brush for any isolated stubborn deposits that require brief mechanical attention. Paper towels, or a clean dry cloth for the drying phase. That is the complete list. The total cost of consumables per cleaning session is well under $3, and the results, as will be seen, are indistinguishable from professional service cleaning. Restoration phase number 1, filter removal and pre-assessment. With supplies gathered, the first action is removing the filter from the range hood. On the vast majority of residential range hood models, this is a tool-free operation. There is typically either a spring-loaded latch on the underside of the hood, push it inward, and the filter panel drops down and slides free, or a simple sliding track that allows the filter to be pulled directly downward and out. Once removed, hold the filter horizontally at eye level and observe the mesh. Notice the density of the deposit and whether the mesh holes are partially or fully occluded. This pre-assessment is not just visual. It tells how many soak cycles will be needed. Light to moderate buildup. A golden brown film that has not yet reached full occlusion will respond completely in 1 7-minute session. Heavy or severe buildup, dark brown or black deposits with mesh holes that are noticeably blocked, may benefit from 2 consecutive soak cycles. Set the filter aside and proceed to solution preparation. Restoration phase number 2. Solution preparation and deployment. Fill a large pot with enough water to submerge the filter and bring it to a full, rolling boil on the stove. While the water is heating, position the roasting pan or container in the sink or on a heat-safe surface. Place the filter inside the container. Once boiling is reached, put on rubber gloves and carry the pot to the container. Pour the boiling water carefully and deliberately over the filter, covering it as completely as possible. If the filter cannot be fully submerged, pour to maximum coverage and allow the process to run. Then rotate the filter halfway through the soak to ensure even treatment. Immediately while the water is still at maximum temperature, add a quarter cup of baking soda directly into the water. Observe the reaction. The baking soda will fizz and effervesce as it interacts with the hot water. This is the release of carbon dioxide gas as the bicarbonate activates and begins raising solution pH. This visible reaction is the saponification process beginning. Follow immediately with 1 tablespoon of liquid dish soap. Using a long spoon, gently stir the solution once to distribute the soap without creating excessive foam. The solution is now fully active and ready to work. Restoration phase number 3. The 7-minute soak protocol. Set a timer for 7 minutes. During this window, the 3-agent system described earlier is operating at full capacity. The hot water is penetrating and thermally softening the polymerized grease layers. The alkaline solution is breaking ester bonds through saponification, converting solid grease into water-soluble compounds. The dish soap surfactants are encapsulating liberated grease particles in micelles, holding them in suspension and preventing redeposition. During these 7 minutes, there is no scrubbing required. This is the no-scrub element of the method. Chemistry is doing the mechanical work. Scrubbing at this stage would actually be counterproductive. It would disrupt the solution's contact with the filter surface and reduce the soak's effectiveness. Use these 7 minutes productively. Take a damp cloth with a small amount of dish soap and wipe down the exterior housing of the range hood. Grease accumulates on these surfaces as well, and the warm soapy cloth will remove it with minimal effort. Wipe the underside panels and the area around the filter opening. These surfaces rarely receive focused cleaning attention, and they will benefit significantly from this 2-minute wipe down. When the timer reaches 0, the chemical process is complete. The soak has done its work. Restoration phase number 4, rinse, final scrub, and inspection with rubber gloves on. Lift the filter from the solution. The difference will likely be immediately visible. Grease that was dark and solidly adhered will appear softened, loosened, and in many cases already partially removed or floating free in the solution. Take the filter to the sink and rinse it under the hottest available running water. Use the scrub brush or toothbrush to work across the mesh surface in small circular motions. At this stage, grease will release with minimal pressure. The work the chemistry has already performed means the brush is simply clearing away material that has already been converted and loosened, not breaking bonds itself. Pay focused attention to the corners and frame edges of the filter where the mesh meets the border. Grease tends to accumulate in these recessed areas and may require a few extra seconds of brush attention. However, even in these areas, the resistance will be dramatically lower than any previous scrubbing attempts without the soak. Hold the rinsed filter up toward a light source. Look through the mesh holes. They should be visibly open and clear. Light should pass through the entire mesh surface without obstruction. The metal should appear bright and identifiable as its true material, silver-toned aluminum or the characteristic finish of stainless steel, rather than obscured under a dark organic coating. If any isolated patches of residue remain, apply a small drop of undiluted dish soap directly to the brush and scrub those specific areas under running hot water for 20 to 30 seconds. This targeted direct soap application will address any remaining resistance without requiring second full soak cycle in most cases. Restoration phase number 5, drying and reinstallation. Lay the clean filter flat on paper towels or a clean dry cloth and allow it to air dry for 2 to 3 minutes. Alternatively, pat it dry with a clean towel if reinstallation is needed immediately. The primary concern is ensuring that water is not dripping from the filter when it is returned to the hood, as moisture pooling near electrical components in the ventilation housing is something to be mindful of. Once the filter is dry, slide it back into its position in the range hood housing. In most models, this is the reverse of removal. Angle the filter up into the track or against the latch point. Push upward and inward until the spring-loaded mechanism clicks or the panel seats flush against the hood underside. A clean click or firm flush seating confirms correct reinstallation. Turn on the range hood fan for 30 seconds after reinstallation. This serves two purposes. It confirms the filter is seated correctly. An improperly installed filter will vibrate or produce unusual noise at fan speed, and it demonstrates the restored airflow capacity of the cleaned mesh. The difference in suction performance between a clogged and a clean filter is often immediately audible and tactile. The hood draws air noticeably more powerfully through open mesh than through occluded deposits. The ventilation performance reality, there is a measurable functional dimension to this maintenance task that extends well beyond aesthetics. Range hood performance is measured in CFM, cubic feet per minute, which quantifies the volume of air the hood can move per unit of time. A clean, unobstructed mesh filter allows the range hood to operate at or near its rated CFM. As grease deposits build up and begin to occlude the mesh holes, airflow resistance increases. The fan motor works harder to move the same volume of air. At moderate occlusion levels, CFM can drop by 20 to 30% from rated performance. At severe occlusion levels, the drop can exceed 50%. This reduced performance has real consequences: cooking steam, smoke particles, and combustion byproducts that the range hood is designed to remove from the kitchen air linger significantly longer when the filter is clogged. Odors persist. Grease-laden steam that the hood fails to capture deposits itself on cabinet surfaces, ceiling areas, and wall finishes adjacent to the cooking zone, creating additional cleaning work and long-term surface damage. The visible result is the yellowish, sticky film on kitchen surfaces near the stove that many people assume is simply unavoidable with regular cooking. It is not unavoidable. It is the direct consequence of a clogged filter failing to capture what it should be capturing. A clean filter is not a cosmetic achievement, it is a functional restoration. Maintenance protocol, keeping it clean permanently, now that the filter has been fully restored. A consistent maintenance protocol ensures this level of buildup never accumulates again. The key insight is that grease in its early deposition stage, before polymerization, responds to dish soap and warm water with almost no effort whatsoever. The labor-intensive process described in this video is only necessary because the grease was allowed to polymerize over months or years. Regular cleaning prevents polymerization from occurring. For households where cooking happens daily, a monthly cleaning cycle using this exact method is ideal. The entire process at this frequency takes approximately 3 to 4 minutes rather than 7, because the deposits have not had time to fully polymerize. The soak does the same chemical work in less time on fresh deposits. For households where cooking is less frequent, 3 to 4 times per week, every 6 to 8 weeks is a sufficient schedule. Run the range hood fan every time the stove is in use, regardless of what is being cooked. Even low-heat operations like simmering or warming release lipid aerosols that accumulate on the filter over time. Consistent fan use ensures maximum capture and reduces the concentration of grease particles that escape the filter and settle on surrounding surfaces. A brief monthly wipe-down of the range hood exterior using a cloth dampened with warm soapy water takes 90 seconds and prevents grease from building up on the housing panels, knobs, and surrounding cabinet faces. What has been accomplished here goes beyond a clean filter. The understanding of why grease behaves the way it does, the polymerization process, the saponification reaction, the role of surfactant chemistry, is transferable to virtually every heavy degreasing task in a home. Oven interiors, stovetop grates, exhaust fan covers, cabinet faces near the stove, all of these surfaces respond to the same chemical principles. The specific agents, concentrations, and contact times may vary, but the foundational logic remains consistent. The range hood filter is one of the most functionally important and most chronically neglected maintenance items in a residential kitchen. It operates silently, it is rarely visible, and its degraded performance produces consequences that are easy to attribute to other causes. But now there is no uncertainty about what it looks like, why it fails, and exactly how to restore it using $3 worth of chemistry and 7 minutes of time. That is not a trick, that is